Hello and welcome to week 5 of MATH375. So last week we talked about the stochastic integral. We explained that the stochastic integral is different from the Riemann integral. And we showed certain properties of the stochastic integral, in particular, the fact that it is a martingale with respect to the filtration for the Brownian motion, which means as a special case that it has the expected value 0, which is a very important property of the stochastic integral. And that in calculations to do with the stochastic integral, a very important tool for us is the ethos formula or ethos lemma. And we showed several examples of how to do calculations with regards to stochastic integrals. And in tutorial, also last week's tutorial, in our last question, we considered a stochastic differential equation, which means that what are stochastic differential equations? Well, they are integral equations which contain a stochastic integral. So this week we will continue on that topic before we start with our new chapter, which is on pricing. So let us continue then with stochastic differential equations. So I'm sure that all of you have encountered differential equations, which are usually called ordinary differential equations. And after you integrate them, they become integral equations. So the equations that we will consider here are certain stochastic generalization of ordinary differential equations. They are important for us here because we will use these equations to model stock prices. We will use them to model the wealth of the investor. We will use them to model interest rates. Okay, so they are a very important modeling tool for us. So that is why we consider them here. So what are these? So if you have an equation that has this form, which means that you have a certain constant x of 0, plus you have an integral, which is a Riemann integral, plus if you have a stochastic integral. So if you have a process like this, so x of t is a process, however, where the process appears also here, you see, and here. In other words, this is an equation where x is the unknown. Well, these equations are called stochastic integral equations if they have this integral form. However, you can take the differential of both sides, and the differential cancels the integral, and this equation becomes a differential equation. More precisely, a stochastic differential equation. So this is these equations are of interest to us. Here, mu and sigma are some suitable functions of s and x of s. And I say suitable is that they can have different forms, but in order to guarantee the existence of solutions, these have to be restricted. But for the moment, it's not important for us to make these objects very precise, because we will only consider examples of these equations. Okay, so equations of these types are called stochastic differential equations. And with any equation, we are interested in finding its solution. It so happens that the solution to these equations are stochastic processes. Okay, so if you remember when you did ordinary differential equations, then the solutions to such equations are functions. For example, an exponential function is a solution to an ordinary differential equation. Whereas here, the solution is a stochastic process. As you remember, we have considered stochastic processes in previous weeks. The question is how to find the solution to such an equation. Of course, by a solution, we mean a process such that when you substitute it into the equation, it satisfies that equation. And of course, here we have the initial condition is specified, or it is given. Well, just like with ordinary differential equations, there are no general methods to find the solution. There are some general sufficient conditions which ensure that the solution exists and that it is unique, but not methods which tell us how to actually find the solution. That is why there are many numerical methods to solving differential equations, both ordinary and stochastic differential equations. And of course, it is important when you have a differential equation to know whether the solution is unique or not. And this is quite an important question for applications, because in applications, it's not of a lot of use if you have an equation that has more than one solution. Because, for example, we will use the equation to model the wealth. And there's no point to tell to an investor that your wealth might look like this, or it might look like this. In other words, if this equation has more than one solution, it is not very useful in some applications that are of interest to us. That is why we will only consider equations that have a unique solution, only one solution. So as I said, as it is written here, there are known conditions, such as Lipschitz conditions on the coefficients of mu and sigma, which ensure the existence and the uniqueness of solution. Since we will only consider examples, we will not go into those conditions. However, what we will do, we will consider several examples. We will consider several examples of these equations and how to find the solution. We have already considered one example in our tutorial 3. That is quite an important example, an example of a linear stochastic differential equation. And we will use such an equation to model the interest rate in our chapter 3. Another very important example is this example 21. So let us have a look, this example 22, but first we will deal with a very simple equation, which is in our example 21. So let us consider this example. In some way, this might be the simplest stochastic differential equation that we can consider. So let us have a look at it. So suppose we have two processes, mu and sigma, for which we assume that they are adapted to the filtration and they have certain integrability. In other words, the first process is integrable, whereas the second process, sigma, is square integrable. And you can see why do we require for this to happen? Because as you can see, if we integrate both sides of this equation becomes this equation. Now, in order for this integral to make sense, this process must be integrable. And similarly, in order for this integral to make sense in the sense that we have defined last week, this process here must be square integrable. So that is why we make these two assumptions. Before we go that, however, let us analyze a bit this equation. So we are given this stochastic differential equation. So this is a Brownian motion. And the question is how to find the solution to this. Well, this equation is very easy. And the reason is because you see the unknown x does not appear either in mu or in sigma. So in other words, we can solve it by simply integrating both sides. So if you integrate both sides of this equation from 0 to t, from this you get this. And this is actually the solution. This is the solution to this equation in an explicit form. There are a few things to notice here. The first thing is that the solution is indeed a stochastic process, because as you can see, this is a random in general, and this is random in general. So even if sigma is constant, this is a process. So solutions to stochastic differential equations are stochastic processes. That is the first point. The second point is that actually this is really the only equation that we can solve. In other words, more complicated equations, we try to reduce it to this one. Okay, and if you recall from last week's tutorial, that is precisely what we did. So using Ito's formula, we reduced a linear stochastic differential equation into an equation of this type, which we could then simply solve. And that is what we will do even in our next example. So as you will see, we will reduce, let's say, more complicated stochastic differential equation into this equation. Okay, so this example is particularly important for us in this module, particularly important because using this equation, we will model the stock price. Okay, so it is quite an important equation for us. So let us have a look at this equation. So suppose that we have, again, two processes, mu and sigma, which we assume that they are adapted and have some integrability. So mu is integrable, sigma is square integrable. And we consider the following linear stochastic differential equation. So you have dxt is equal to mu xt dt plus sigma xt dw. Now you have, in case any one of you doesn't know why am I using this word linear, it means that the unknown x in this equation appears linearly. In other words, you don't have here a square, let's say, or a third, or some other non-linear function. That is why we call them linear. In this week's tutorial, you will see an example of a non-linear stochastic differential equation. What is important here, however, is that you see the x appears both in the, let's say, the drift. This term is called drift. This is called the diffusion. So it appears both here and here. If you compare this equation with the equation of last week's tutorial, there we didn't have an x here. So this is a different equation from what we considered before. And very also important is that here we assume that the initial value is positive. Initial value is positive. Now it can be shown by different methods that this equation has a unique solution, only one solution. Here we are interested in finding that solution. How should we find the solution? Well, we will try to reduce it to the previous equation, this one. The question is how? The question is how. The method is actually very similar to how you would solve this equation if this sigma was 0. So in other words, if you didn't have this term. So if you remember from, let's say, first year study, what you do is really you take the derivative of a logarithm of x. Here, since we cannot, since these are stochastic processes driven by a Brownian motion, which is not differentiable, rather than taking the derivative of the logarithm, we apply Ito's formula to the logarithm. Okay, so let us assume that, and of course, in order for the logarithm to be well defined, we must assume that x is actually positive. Otherwise, the logarithm will not be defined for, will not have real values, more precisely, if x can take negative values. So let us assume that the solution is positive, and let us apply Ito's formula to the logarithm of x. And you will see that the effect of applying the logarithm of x is because these x's here and here will cancel out. So if you apply Ito's formula, so the first derivative with respect to time is 0. The first derivative with respect to x is 1 over x times this part here, which is here, plus 1/2. The second derivative of logarithm of x is minus 1 over x squared. We have always the 1/2 times whatever you have here, so the diffusion but squared, dt, plus the first derivative of log x with respect to x times this whole thing here, which is sigma t x t dwt. Now notice that these x's will cancel out. and the equation reduces to this form. Now, as you can see, in this form, there is no x either here or here. So in other words, this is an equation of the form that we have seen before. In other words, of this form. That is why we know how to solve this. We simply integrate both sides from 0 to t. So if you integrate both sides from 0 to t, here, if you pay attention to this part here, the integral cancels the derivative, and this becomes this. So this will remain the same throughout these steps. You can put the two logarithms together to get this. And if you get rid of the logarithm, this becomes x0 e, or exponential, into this power. And this is the actual solution to this equation. If it happens that mu and sigma are constant, then this reduces further to this form. Now, I am sure that you have seen something like this already in this course. If you remember, when we were calculating certain expected values, we used something very similar to this, but instead of small t, we use the capital T. And there is a good reason for this, because we will use this, the solution to this equation, as our stock price. Okay, so these are a couple of examples of stochastic differential equations and how to solve them. Let us see one more example. So once you find the solution, that is a stochastic process, and now you might be interested to know what is the expected value of that, or the variance of that. So let us see one such an example. So example 23. Example 23 actually gives us something called the mean reverting property. Okay, but let us see what that is. So let us consider this linear stochastic differential equation. So this equation is the same as what we considered last week in our tutorial 3. So we know that its solution has this form. In this example, what we are interested in is how does its expected value behave as t goes to infinite. So what is the behavior of the expected value of x? Now, of course, if we take the expected value, the question is how to find the expected value of x. Simply take the expected value of both sides of the equation. Now, keep in mind, this part is completely deterministic. This part is also completely deterministic. Expected value of the stochastic integral is 0. That is why, if you take the expected value of both sides, you get the following. Okay. So you get precisely, so the stochastic integral, expected value of stochastic integral is 0. Now, if you integrate through this part, okay, so you get this final expression. As I already said, in this example, what we are interested in is what happens to the expected value as t goes to infinite. And under the assumption that a is negative, and what happens regardless of the initial value. So regardless of the initial value, what is the behavior of expected value of the solution as t goes to infinite? Well, we can distinguish two cases. So pay attention here. If x of 0 is actually minus b over a, then these two terms will cancel out. And what you get is simply minus, so if the initial value is like this, then xt, if this and this cancel, will be simply minus b over a. So it remains constant. Solution remains constant. If on the other hand, the initial value is different from this, so if the initial value is different from minus b over a, then again, the solution will not be constant. However, it will converge to the same value. So as you can see here, the solution will converge to this value as t goes to infinite. Well, this kind of the behavior is called the mean reverting property. So in other words, regardless where you start, so regardless where the process starts, its expected value will eventually revert, go back to this value, to the value minus b over a. So in other words, the expected value reverts or will return to the value minus b over a. We will see that another important model, the so-called CIR model, has this property, and we will see this in this week's tutorial. Okay, so with this actually we finish this chapter 1, where we have built, I would say, very good foundation on probability theory and stochastic analysis. From this point on, we will only actually work with, we will only consider mathematical finance problems. However, we will use these tools from probability theory throughout. So let us begin now with the second chapter. So the second chapter is, as you can see, on pricing and hedging. So in this chapter, we really solve one of the most basic problems of mathematical finance, namely the deriving of the so-called risk-neutral pricing formula. So risk-neutral pricing formula gives us the price of a derivative security. And that formula I have already mentioned in our very first week. And it is in this chapter that we actually derive it. And we will use it in this chapter to price contract, but we will use it also for the remainder of this module. Okay, so what is the main problem that we are trying to solve? Well, let us first talk about the market in which we work on. Okay, so let us consider a probability space. And on this probability space, we have a Brownian motion, which is defined on it. And throughout this chapter and for the remainder of this module, we will always assume that our filtration is the natural filtration of Brownian motion. So in other words, the filtration generated by this Brownian motion, which is an example of the filtration for the Brownian motion, which we have encountered in the previous chapter. So this is our, let's say, the probabilistic setup. So we have a Brownian motion. And we will consider a market of only two assets. Okay, so the first asset, we will call it a bank account. We will call it a bank account, and it has the following price. Okay, so the price of the bank account is given with this equation, which is actually an ordinary differential equation, but with this coefficient R of t, which can be deterministic. In other words, this equation does not have this dw term. And this process R of t is called the interest rate. If R is actually constant, this is a model of the bank account that has a continuously compounded interest. Okay, so that is really why it is called a bank account. But for us, it is simply one of the assets in our market model. So this is the first asset. It is a bank account. And we assume that R of t has sufficient integrability for this equation to have a unique solution. As our second asset that we have in this market is an asset with a price S of t, which we call the stock. And it has this equation. So the solution to this equation is the price of the stock. Now, I'm sure that you can immediately recognize that this is the equation that we considered in our previous chapter, for which we found the solution of it. And what is important is that this equation has an explicit solution, and the solution is positive. This is important. The coefficients mu and sigma, again, are some adapted processes with sufficient integrability. Mu is usually called the expected rate of return, whereas sigma is usually called volatility. Okay, so this is our market. So we have a market with only two assets. Almost everything that we say in this chapter will be valid even for a more general model with multiple assets. But for us, for the purposes of this module, this model will be sufficient. Okay, so we have a market with two assets. Now imagine that in this market we have an investor. Okay, so an investor can hold a certain number of shares of one asset and a certain number of shares of the other asset. So we will denote by VBT number of shares of the investor in this asset in the bank account, and VS of T the number of shares of the investor in the stock at time T. Now VBT can take both positive and negative values, so depending whether you are depending whether you hold the stock or you short sell the stock and so on. So VPT and VS of T can have both positive and negative values. Now, of course, if this denotes, if these processes denote the number of shares, then the portfolio value or so because of course the total number of shares that an investor holds, the total number of assets, that an investor holds, that is his or her portfolio. The value of that portfolio is, of course, given by this equation. So the number of shares times the price plus the number of shares times the price of the asset. So this is the investor's portfolio value. Now, this pair of processes, VB of T and VS of T, jointly together are called the trading strategy of the investor. And we will always assume that they are adapted to the filtration. In other words, their value depends only on the information that we have up to time T. So not on information which we don't have at time T, which could be something depending upon the future. For us, will be particularly important the following type of portfolio, namely the so-called self-financing portfolio. Okay, so a portfolio will be called self-financing if it satisfies this equation. What does this mean? It means that this change in the wealth will occur only due to the price changes. Okay, only due to the price changes. In other words, a self-financing portfolio is a portfolio where we neither input extra wealth or neither do we take out any wealth. Okay. So this is our market model that we will consider. Now, what is the main problem that we would like to do? As I already said, we would like to price derivative securities. Well, let us see first what are these derivative securities and how should we price them. Okay. So as you can see, our main concern in this chapter is to price derivative securities. What are these? Well, derivative securities, as I have already said in week 1, are certain financial contracts whose value depends upon the price of some underlying asset. Or more precisely, a derivative security is a financial contract whose value at expiration date T is determined exactly by the price of the underlying asset at time T. Okay. Okay, you can have it in general. In general, you can have it that the price depends not only upon the price of the underlying at time T, but also on previous values. So this is quite, let's say, a general definition of what is a derivative security. The asset, the underlying asset is simply called an underlying. Okay, so this is, I would say, quite a general definition of what is a derivative security or a financial derivative. As an example, as a very important example of derivative securities are options. So let us give a definition of what is an option. Okay, so an option is a financial contract giving one the right but not the obligation to make a specified transaction at or by a specified date at a specified price. Of course, when we talk about financial contracts, by transaction we mean to buy or sell something. Okay, and whenever an option gives you the right to buy, let's say, an asset at a specified time, that is called a European option. Whereas if it gives you the right to buy something but not the obligation by a certain time, then that is an American option. That is why you have this general definition. So this is again a general definition of what is an option, whereas a particular special case of an option is a European call option. So let us see what this is. So European call option gives the holder the right but not the obligation to buy 1 unit of an asset, let's say our stock that we mentioned before, at time t for the specified price k. Okay. So this is an example of a European option, so European call option. Now we immediately come to the problem of how to price, how to find the price of this contract, but at a certain earlier time. Since, of course, we will use mathematics to do the pricing, the first thing that we need to do once you have the description of a financial contract is to translate that into mathematics. Because without making this first basic step, you cannot use the mathematics machinery to do the pricing. So this is the first thing that we have to do. From the textual description of the financial contract, we must write the mathematical description of the financial contract. Now, for this particular case of a European call option, its terminal value, so the value of this contract at time t, should be like this. Suppose that the underlying asset is S of t. Suppose that the underlying asset is the stock, and the contract gives its holder the right to buy the asset at time capital T for the certain price K. Now, of course, the holder of the contract will exercise the option only if it makes a gain out of it. Otherwise, he or she will not exercise the option. So that is why you get for the terminal value of the European call option the following form. So the investor will pay K, that is why you have minus K, and will obtain 1 share of the stock. That is why you have the stock with the value plus. And it is, of course, the maximum between these two, because between these two, because the holder of the contract will exercise the contract only if this is positive. Otherwise, he or she will not exercise the option. So this is the first step. From the description, we come up with a mathematics that describes that. A very important thing to note is that the terminal value is actually a random variable, because if you remember, we modeled the stock price as the solution to a certain stochastic differential equation. So S of t is actually a random variable. So that is why some function of the random variable is also a random variable. Moreover, st, as you have seen even in the example that we did earlier, is in general, well, st is actually ft measurable random variable, where f is the natural filtration of Brownian motion. Okay, so the most basic contract, one of the most basic options, the European call option, mathematically is an ft measurable random variable. So this itself immediately justifies all the let's say, hard work that we have been doing in the past 4 weeks in building our probability foundation. Because if we haven't built such a foundation, we wouldn't be able to understand what this is. Okay, so of course, this is not the only example of the option, and there are many examples of the option like this, but this immediately implies that we should consider a derivative security from the mathematical point of view as some FT measurable random variable. Okay, so from this point on, for us, a derivative security or a financial derivative mathematically is simply a random variable x that is in general FT measurable. So this is how mathematically the contract is defined as a random variable. Now, so we already know what is the market, what is the market model, what are the financial contracts that we would like to price. The most basic question is now as follows. So what should the price of a derivative security, xt, be for t less than capital T? So this is the most basic question that we will answer in this chapter. And we will consider one way of pricing this. And this is the way or the method implied or suggested by the so-called arbitrage pricing theory. So first, we have to explain what is an arbitrage. So the arbitrage means the possibility or the opportunity to make a riskless profit. Okay, so to make a profit without any uncertainty or a risk. So in other words, this is used as a basic principle when pricing in the arbitrage pricing theory. In other words, you should price a contract in such a way so that when you place such a contract into a market, it will not create arbitrage opportunities. So it will not create the opportunity to make a riskless profit out of your contract. Okay, but however, we need to make the notion of arbitrage more precise. That is why we have the following mathematical definition. So mathematically, an arbitrage is as follows. So an arbitrage is a self-financing portfolio value process that satisfies the following properties. So y0 is equal to 0, and for some time t greater than 0, the following two conditions hold. So the probability of yt to be greater or equal to 0 is 1, and the probability of yt to be positive is positive. What does this mean? This means that, so you, first of all, you already know what is a self-financing portfolio. So we have given the definition of this earlier on. Now, if there exists such a portfolio, so a self-financing portfolio, which will start with a zero value, And in the future, there exists sometime in the future such that for certain, so with probability 1, the value of such portfolio will not be negative. Okay, so you start with 0, you are certain that you will not go below 0. However, there is a positive probability that the value of the portfolio will be positive. If that is the situation, such a portfolio is called an arbitrage. So in other words, if you have a market where you can construct a self-financing portfolio that has these properties, then we say that there is an arbitrage in such a market. Okay, so the question is of course, is arbitrage good or bad? If you are an investor, then arbitrage is certainly good. So you would like to exploit the arbitrage. In other words, you would like to exploit this opportunity to make a riskless profit. However, if you are in the position of pricing a contract, then you certainly would like to price the contract in such a way that you do not create arbitrage opportunities. Okay. It so happens that in our two-asset model, in our two-asset market model, under the conditions that we would place, there do not exist arbitrage opportunities. In other words, in our two-asset market, it is impossible for you to construct such a portfolio. Okay. However, there are certainly market models where you can construct a portfolio that is an arbitrage. In fact, you will see this in this week's tutorial, that is the case. In practice, arbitrage may exist, but it disappears very quickly because investors that exploit that, at the same time, they diminish that. Okay, so that is the situation. So we will show later on in this chapter that in our two-asset market model, there does not exist an arbitrage. Okay, so this fact actually immediately suggests how we should go about in answering this question. So why don't we model the price of a financial derivative as simply as a self-financing portfolio? Okay, because for as long as we have it as a self-financing portfolio, that will not be an arbitrage. Okay, because and this is the situation in this two-asset market. The next question is, of course, immediately comes is that which self-financing portfolio should we pick? Because as you know, for every, just to remind you very quickly, you see the self-financing portfolio depends upon this VBT and VS of T. For different pairs of such, you get different self-financing portfolios. The question is which VBT and which VS of T should we actually employ for our self-financing portfolio of our derivative security? Well, the minimum that we should require. Okay, so you see here you have the question. So the question is which self-financing portfolio? The minimum that we should require is, of course, that the self-financing portfolio must have this value x at terminal time t, because that is how the contract is specified. Okay, so this is the second requirement that we place. So this is the first requirement, actually, that we place on our self-financing portfolio, which we will use as the price of our derivative security. Okay. So as it is written here, in order for a self-financing portfolio to represent the price of a derivative security, it must satisfy this minimum requirement. So YT must be equal to X, because X is the value of the derivative security at time T. And through X, it is actually that this derivative security is defined. Okay. Now, this immediately poses the question or the problem whether or not there exists such a trading strategy that ensures this. Well, this question can be formulated precisely as follows. So consider the following stochastic differential equation. Different from the differential equations that we saw in chapter 1, please note that here it is actually the terminal value that is specified, so not the initial value. So we have an equation where the terminal value is specified. These equations are called backward stochastic differential equation because you must solve the equation backward in time, not forward as we saw in our chapter 1, but backward in time. So in other words, if this equation does have a solution, in other words, if there exists a VBT, Vs of t, and Y of t such that this holds, then indeed we do answer the question that we posed before. Okay, so we do answer this question. Which self-financing portfolio? Okay, so the self-financing portfolio that achieves this. And if we can solve this, or in other words, so later in the chapter, we show using the martingale representation theorem that this actual equation does have a unique solution pair. You see, by a pair, we actually mean this y of t and this trading strategy. So this is what we mean. So we will show this that this equation does have a solution. Moreover, the solution to this equation is unique. And this pair, VPT, VST, is actually called the hedging strategy. Okay, and we show that this equation has a solution using the martingale representation theorem. So recall that last week we did introduce the martingale representation, and the reason why we introduced it is precisely in order to show that this equation has a solution. Okay, so this will be it for this week, but just to mention that next week, we will have to show a couple of things. First of all, we will show that what we promised in this week, actually, that in the market with two assets, there is no arbitrage, and that there exists a solution to this equation. Okay, so that would be it for this week.